So we're going to talk about the probability or the likelihood of various events occurring. So this is a very practical application of mathematics where you're able to, make a choice, make an informed decision based on a probability or a chance of something occurring. There's some people who take chances with things like the stock market or cryptocurrency or a lottery, things like that, or gambling, right? There's probabilities, there's chances of success that you could win or you could lose. Or maybe if you decide to go out without an umbrella, there's a chance that you could get rained on, right? And so like weather forecasters make predictions based on probability and chances of certain meteorological events occurring. And so we're going to talk about just some simple cases here, some basic probabilities, and learning two different rules of probability. So the first target is this addition rule of probability. And we're going to talk about multiple events occurring, not just the probability of one thing happening, but of multiple things happening. First off, though, let's go through just some basics. So a basic probability, the way that it's written is capital P and then parentheses of some event occurring. So the probability of some event occurring. And it's going to be a basic fraction. And this fraction is considered, in the numerator, you basically list the number of favorable outcomes, meaning the thing that you want to have happen. So for example, take something simple like rolling a 6-sided die, and I want to know what's the probability of rolling a 2. Well, the favorable outcome would be rolling a 2, right? How many sides on that die would have a 2? That's what I want to have happen. The denominator is going to be the number of possible outcomes. So, well, how many different things could happen? And just logically, that's kind of what you would expect our probability to be. What are the chances or what's the probability of rolling a 2? Let's actually calculate this. So I'd say P, and then in the parentheses, the event is rolling a 2. And you're just going to make a simple fraction. Well, how many sides on a die have the number 2 on them? Just one, right? There's only one side with the 2. So how many favorable outcomes are there? Well, there's only one. There's only one good outcome there. There's only one chance of that occurring on a 6-sided die. But how many possible outcomes are there on a 6-sided die? 6 of them altogether. So that's your denominator. So there's one chance out of 6 possible chances. And you just divide this out. And what do you get? What's 1 divided by 6? You can use a calculator if you want. No? You have it right in your hands. I know it's tough. You have to hit 1, 2, 3. What is it? 0.16. So your probability, 0.16. Now, it's important to note that your probabilities are going to be decimals. What's the smallest possible number you could get for a probability? Go ahead. 0.01? Think you could have less than that? Could you have a probability of even 0? Like, how about on a 6-sided die with the numbers 1 through 6? What's the probability of rolling a 7? On a standard 6-sided die, how many of the sides have a 7 on them? 0 of them, right? Well, there's no chance out of 6. So that is a probability, that's a 6, of 0.000, just 0. So you can get as low as 0. Could I get negative probabilities ever? No, not at all. So 0 is the lowest number. What's the largest probability that you could ever have? Could you get 1.0, do you think? Can you give me an example? 6 out of 6? Or how about the probability of rolling a 1, 2, 3, 4, 5, or 6, right? What's the probability of rolling one of those numbers on a 6-sided die? Well, they all have that. So there are 6 favorable outcomes out of 6 possible outcomes, right? Numbers 1 through 6. So if you divide that out, you get 1. So your range in probabilities is anything between 0 and 1. Typically, it's going to be some decimal in between that. Just like we got with the probability of rolling a 2, we had a 0.16. Now, the closer a number is to 1.0, the more likely it is to occur. What about this number, 0.16? Is that closer to 1 or closer to 0? Closer to 0. So is this likely to happen? No, that's not that likely to occur. Right? That's a low probability. It's not too likely that's going to happen right away. So this is how we denote probabilities, and that's the standard way of calculating a single probability of a single event occurring. Today, we're going to talk about the probability of multiple events occurring. And so to determine this, we first need to decide if these 2 events that are going to be occurring are what's called mutually exclusive. The word exclusive, have you heard that before? Like something that exclusive means like it's rare, it's one of a kind, it's separate. So mutually exclusive simply means that they can't occur at the same time. So here's an example of a mutually exclusive event. If I roll a standard 6-sided die, then the events of rolling a 2 and rolling a 3, can those both happen at the same time if I roll one single die? Can I roll a 2 and a 3 at the same time? No, it's impossible, right? They can't both happen. So that's considered mutually exclusive. Those probabilities are completely separate. They're not going to both occur at the same time. You okay with that concept? Mutually exclusive, very common term in probabilities. We need to know that because if 2 events are mutually exclusive or not will affect the formula that we use to calculate that compound probability of these multiple events. 2 events are not mutually exclusive if they can occur at the same time. So something that's not mutually exclusive, here's an example down here. Imagine I've got a deck of playing cards, and if I draw one card from a deck of playing cards, then the events of drawing a diamond and drawing an ace. Well, those 2 events aren't mutually exclusive because couldn't they both occur at the same time with a single draw? Can I draw an ace and draw a diamond at the same time? Because there are 13 cards with diamonds. One of them is an ace. Right? I could draw the ace of diamonds, meaning it would be both of those things. So both events could occur at the same time. They don't have to. I could draw a diamond that's not an ace, or I could draw an ace that's not a diamond. But I could draw the ace of diamonds, which means I'm going to have both events occurring. Therefore, those events are not mutually exclusive. Right? Exclusive means it's like it's on its own, it's by itself. It's the only way it could happen. But these are not mutually exclusive. They could both occur at the same time. All right, just kind of help you conceptualize that. So here's your addition rule of probability. And there's 2 different formulas that we're going to use that you need to have written down in your notebook. And the formula that we use is going to differ based on whether or not these 2 events are mutually exclusive or not. So go ahead and make sure you've got these 2 written down. So this is the addition rule of probability. First off, for mutually exclusive events, meaning 2 different events that could not occur at the same time, then we would write, and the left side is just the probability of the events occurring. So the probability of event A or event B occurring. So it's like, what's the probability of rolling a 2 or rolling a 3, right? Those are mutually exclusive because I can't do both at the same time. And the way I'd calculate that probability is I would just I'd calculate them both separately and then add them up. So I'd figure out, well, what's the probability of rolling a 2? Figure that probability out. Then find the probability of rolling a 3, calculate that one. Then just add them together, and that would be the probability of rolling a 2 or a 3. Because those are mutually exclusive events. Now, if two events are not mutually exclusive, then the probability of one event or the other event occurring, it's very similar, but there's one change that we have to take into account. So if you look at this, probability of A plus the probability of B, that's the same as the mutually exclusive option, but there's one additional part to it, and that's this subtraction of the probability of A and B occurring. So you have to subtract that out. Now here's why. Just make sure you've got this written down somewhere, that formula, because we're going to be using it. Let's go to my ace of diamonds example. So we'll say probability A is drawing a diamond, and probability B is drawing an ace. A standard deck of cards has 52 cards. There are 4 different suits. Those are the symbols on the cards. There's diamonds, hearts, clubs, and spades. Each suit has 13 different, numbers or letters on it, 2 through 10, and then a jack, a queen, a king, and an ace of each of the 4 suits. And those are the 52 cards altogether. So if I want to calculate the probability of drawing a diamond or an ace, well, first let's calculate the probability of each of them occurring separately. So the probability of drawing a diamond. Do you remember how many diamonds are in a deck of cards? It's 13 of them. So the probability of A, of drawing a diamond, equals, so the number of favorable outcomes is 13. And how many possible outcomes are there in a deck of cards? There's 52, so that's our denominator. So that's the probability of drawing a diamond. And the probability of drawing an ace. How many aces are in a deck of cards? There are 4 of them out of the same 52 deck of cards. So those are my 2 separate probabilities. Now, if those events were mutually exclusive, I would just add these 2 probabilities together, which you can do nice and easy. Common denominator. I love that with fractions, right? But there's an issue. Let's take a look at a little diagram to represent this. If this circle represents all the different diamonds in the deck, there are 13 of them. All right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. This circle here represents all the aces in the deck. And there's 1, 2, 3, 4. You'll notice that all my aces and all my diamonds, there's one overlap, isn't there? There's one card that is both an ace and it's a diamond. And so my probability needs to add up all the dots in these two circles. And if I add them up, over in just the red circle, there are technically only 12 of them, right? Because that one's in that double shaded zone. Over here, there are 3 of them, plus there's one more in the middle. And we don't want to count that dot in the middle twice. I don't want to count it for the diamonds and for the aces. So because of that, I have to subtract it out. And that's what this subtraction piece is doing. The probability of both of those events occurring, that probability is this overlap. It's where there's a diamond and an ace when they're both there together. And so if I add these up, I get 12, 13, 14, 15, 16 possible cards that would make that true. Now, if I just add these up, 13 plus 4, that gives me 17. But I counted this one in the middle 2 times. I counted it as part of the diamonds and I counted it as part of the aces. So I have to subtract that off, that double occurrence. I have to subtract it from that total. And so then the probability of diamond and ace equals, there's only one card in that deck that meets both of those conditions, a diamond and an ace. So that's the probability of A and B right there. And so then using this formula, probability of A plus the probability of B minus that overlap, minus them both occurring, because we kind of double dipped. We counted that thing twice because it wasn't mutually exclusive. So when I add these up, we've got 13 out of 52 plus 4 out of 52. But then I have to subtract this overlap area where they're both an ace and a diamond. And that's just 1 out of 52. You calculate that. Luckily, these fractions are nice and easy because they have a common denominator. I love that, right? And you're just adding the numerators. 13 plus 4 is 17. Minus 1 is 16. And so then your probability of drawing an ace or drawing a diamond is 16 out of 52. Or if you divide it out, 16 divided by 52, we get 0.31. So that's the probability of drawing either an ace or a diamond from a deck of cards. All right, I'd like you to calculate this. Try this one on your own, everybody. So, what's the probability of rolling a 2 or a 3 on a 6-sided die? So the probability of rolling a 2 or rolling a 3. Now we do have 2 formulas to choose, and that's going to depend on if these events are mutually exclusive or not. So first, tell me, are these mutually exclusive events, rolling a 2 and rolling a 3? What's that? So rolling a 2 or a 3, right? Can those both happen at the same time? No, they're independent events, right? They're separate from each other. They can't occur at the same time. And so I don't need to subtract that overlap because I couldn't roll a 2 and a 3 at the same time. Okay. You sure? You seem like you want to say something. It's okay if you want to. Okay. That'd be a first. So these are mutually exclusive events. They can't occur at the same time. So what's the probability of rolling a 2 or a 3? So you're going to want to calculate those probabilities separately. You're going to want to get a calculator out, by the way. Because we're going to be getting a lot of decimals. So look at the formulas. There's only two of them. Nice. Mm-hmm. Yeah. I'll just divide it out. Awesome. Good. Yeah. Yeah. Yeah, nice. So since these are mutually exclusive events, we're going to calculate the probability of each of them separately and then just add them up. We don't need to subtract anything because there's no overlap. I can't roll a 2 and a 3 at the same time with a single die. Not going to happen. So the probability of rolling a 2, well, that means there's one favorable outcome because there's only one 2 on a 6-sided die out of 6 possible outcomes. For the 3, same exact probability, right? There's one side with a 3 on it out of 6 possible sides. And so you can either add these up as fractions first or divide them out and add up the decimals. You're going to get pretty much the same thing. And so then the probability of rolling a 2 or a 3 is simply 1/6 plus the other 6, right? That's the probability of the 2 plus the probability of rolling a 3 for a total of 2/6, which is the same as 1/3. If you divide that out, you'll get approximately 0.33. If you divided them out first, you'll probably get 0.32. That's fine. It's close enough for me. Also, because these probabilities are always a number between 0 and 1, and usually some decimal, you'll often see them written as percentages, because 1 would be 100%, 0 would be 0%. So if you ask, like, what are the chances of you rolling a 2 or a 3, simply move the decimal over 2 spots, and you'd say, oh, there's a 33% chance that you would roll a 2 or a 3 on a die. Uh-oh, I already did this one for you. Let's change it up. Probability of drawing, instead of a diamond, make this a red card. So what's the probability of drawing a red card or an ace? Ooh, we have to think a little bit. I thought maybe I'd have a deck of cards here to show you, but I don't. So half the cards in the deck are red, half the cards in the deck are black. The ace, there are 4 of them. Half of them are red, half of them are black. So see if you can figure this one out. Are these events mutually exclusive? Or could they both occur at the same time? Could I draw a red card that's also an ace? So these are not mutually exclusive events. right? Because they aren't occurring separately. They could both occur at the same time because there are some aces that are red. So we have to consider that overlap. So go ahead and calculate it out. Make sure you're using the correct formula. This would be that second one. Good. If you keep this as out of 52, then it's easier to add because you have a common denominator already. So it is 1/2, but just leave it as 26 over 52. That way, super easy to add. You're welcome. Yep. So there are 2 red aces, though. Because of the 4 aces, 2 of them are black and 2 of them are red. So your 3 probabilities you need to calculate: probability of a red card, probability of an ace, and the probability of drawing a red ace, because that would be both of those occurring. And the probability of drawing a red card, well, half the cards in the deck are red. So that's 26 possible cards that are red out of 52 total cards in the deck. The probability of drawing an ace, well, we know that there are 4 aces in the deck out of those 52 possible cards. So normally I just add those 2 probabilities together, but that actually has additional cards. There's some overlap between those 2 because some of these cards are added twice. Because the probability of drawing a red ace, well, that's 2 cards out of 52 are both red and an ace. So I have to subtract that out because I double counted it. I counted it with my red card total and I added it with my ace card total. Because there's 2 cards that are in both of those sets. I can't count that twice. So for my total calculation here, I'm going to add up the probability of event A, which is drawing just a red card, plus event B, which is drawing an ace. But I had to subtract this overlap because I counted those aces that were red 2 times. So I had to subtract that part. And again, these are so nice when they have the same denominator because I know it's over 52. 26 plus 4 is 30. 30 minus 4, or I'm sorry, 30 minus 2 is 28. Divide that out. 28. 52 is 0.54. Anyone else get that? So 0.54 or 54%, if you want to think of it that way. So is that a pretty good probability? It's a little bit more, right? A little bit better than half. So slightly more likely to occur than flipping a coin, which is exactly 50% of getting a heads or tails. All right, any questions on this addition rule of probability? Just add them up, but if they can occur twice, if there's overlap, then you subtract that overlap off. That's really all there is to this rule. Pretty cool? Any other questions on it? Is this pretty nice and easy? Do you like this one? Yeah, Good way to end the year, right? All right, so this is called a two-way table, which is a nice way to display multiple types of information where there's two different categories and groupings that we see in multiple rows and multiple columns. So this is a more useful, more realistic application of it. People aren't actually using advanced probability techniques to calculate, rolling a die. Well, at casinos, I guess. But for us, here's an academic application. So for the last test, some students studied for it, some students didn't study. Of all those students, some of them passed the test and some of them didn't pass the test. Now, just because you study for a test, does that mean you're going to pass it? It's not a guarantee, right? You could study and still fail. Maybe you studied poorly or you studied the wrong stuff, or maybe you looked and you still just couldn't get it. But also, if you didn't study, you probably didn't pass. But is there a chance that if you didn't study, you will still pass? Yeah, don't you hate those students, the ones who just don't look at their notes or anything and they just get it right away? Or they're the worst. So this is kind of showing that whole grouping. And I want to know, what's the probability that a student either passed the test or that they studied? All right, what is the probability that the student passed the test or they studied? Go ahead and try to figure that out from this table. Take like a minute, 2 minutes. See if you can read that table. I'm not going to kind of go into any more detail about this table yet, but see if you can look at it and figure that out. Before you decide what to use, are those two events mutually exclusive? Passing the test and having studied for the test. Go ahead and calculate that probability. And be careful how you calculate the total number of students. You got the right total? Nice. Yeah, you got it. Yep. Good. Check your total again. Yes. No, our last test, those numbers will be much lower. No, I just made this up. Ideally, if it was one of my classes, it would be, like 28 passed, and 0 didn't pass, and 0 didn't study, and 0 didn't pass the study. That's what my number would be like, right? Everyone studies for their test, and everyone passes. Isn't that how it works? 100%. It's exactly how school works. Unfortunately, I think more of our students fall into this category. Eek. More so just because students don't know how to study. They think, oh yeah, I looked at my notes, like literally just flip through the pages, and they go, that's studying. Wow. All right, so first off, are these mutually exclusive events? They are not. They are not mutually exclusive because they both could occur at the same time. Meaning, I could have a student who passed and who also studied, right? There's overlap there. They both could occur at the same time. And so I need to calculate each of those probabilities separately and then subtract that overlap probability. So first, what's the probability that a student passed? Right, that's the first group. So how many total students passed? Is it this 15 right here? No, pass is this entire column, isn't it? Isn't that the list of all the students that passed? So how many total students is that? That's 20. You add them up, right? 20 total students who passed out of, how do you get the total number of students? So if I look at this column, there's a total of 20 students who passed, right? Some of them studied, some of them didn't study. How many total students didn't pass? Well, if you look at this column, I have 8 students who didn't pass. Again, some of them studied, some of them didn't study, but 20 students passed, 8 students didn't pass. That means altogether, there were 28 students. So you have to look at each column and then add this up and say, hey, that's a total of 28 students. If you look at the rows instead, you'd get the same number. So if I take my whole class, some students studied, some of them didn't study, right? If I add up all the students who studied, well, 15 plus 2 is 17. And some of the students didn't study, that was 11. And if I add that up, well, 17 plus 11 is also 28. So you look at the two possibilities. Each student is in a group. Either you studied or you didn't study. How many total was that? Or you were in a group that passed or didn't pass. What's the total when you add up all the students who passed with all the students who didn't pass? So we have a total of 28 students. Let me clean this up a little. All right, so the number of students that passed, that's 20 out of 28. And we want to know the probability that the student passed or that a student studied. So how many students studied for the test altogether? So this is my studied category. And how many total students studied? Well, some of them passed, some didn't pass, but altogether there were 17 students that did study for this test. So the probability that a student studied is, well, how many was that? There's a total of 17 students that did study for the test. Out of the number of possible students, that's out of 28. And finally, we need the probability that a student passed and studied. What's that number going to be? Well, that's the easy one. That's just given to me in the chart, isn't it? Passed and studied is right there. That's just 15. There are 15 students who studied for the test and also passed the test. So that's 15 out of the same total, right? Out of the total 28 students. So now we need to use our formula. So I can't just add up the number of students passed with the number of students that studied, because there's some overlap between them. Some of the students who passed also studied, but not all of them. And so I'm going to add up the 20 over 28 plus the 17 over 28, but I had to subtract off this overlapping region of students that both studied and passed the test, because 15 of them are in group A and 15 of them are also in that group B, and so I can't count them twice. All right, all together, you get 22 over 28, right? Is that what you got? 22. And divide that out. And about 0.79. 0.79. So there's a pretty good probability that if I just randomly selected one student from the class, that they either studied for the test or they at least passed the test, which is good. It's a good thing. All right, any other questions on this addition rule of probability? Just out of curiosity, how many of you got the 0.79? Nice. Awesome. All right. And I guess that's it for our lesson today. Wait a minute. Oh, there's a whole new lesson. Yes! So excited. I know, isn't that a neat feeling? When you were like so sad that all you're learning is one thing today, and then all of a sudden, boom, you get to learn 2 things today. Awesome. Best news ever. It is. It's good. All right, so this is your second learning target. It's also pretty simple, pretty straightforward idea. This is called the multiplication rule of probability. Any guesses as to which operation we're going to be using this time? Division, good. Parentheses, yeah, awesome. Square roots, anyone? So in the multiplication rule of probability, whereas the addition rule had 2 different formulas that we would use based on these events being mutually exclusive or not, the multiplication rule depends on 2 events being independent. And there's going to be probability of 2 events or more occurring one after the other. The probability of this occurring and then that occurring. And so we need to determine if these events are independent or not. Independent, that means like you're on your own, right? Like your independence, it means you can survive on your own. That means you don't rely on anyone. Completely on your own. And so events occurring are independent if they also kind of stand on their own. If one event occurring has nothing to do with the other event occurring. So here's an example of 2 independent events. Let's say I'm rolling a die and I'm going to draw a card from a standard deck. These are 2 events. I don't know what's the probability of rolling an even number on a die and drawing a heart from a deck of cards. Now, if I roll that die, if I roll an even number, depending on what I get, an even or an odd number, is that going to change the probability of me drawing a heart from the deck of cards? Does rolling this die have any effect whatsoever on that card selection? Is it going to increase or decrease the chances that I would draw a heart? No, not at all. It's not related at all. They're completely separate events. They are independent from each other. Likewise, if I drew a heart from a deck of cards, well, that's not going to affect what I roll on a die at all. Those are completely independent from each other. They have nothing to do with one another. So these are completely independent events, where the outcome of one will not affect the outcome of the other event. You okay with that? That concept, independence, like totally unrelated. Well, believe it or not, there's a concept called dependent events. Well, two events are dependent if the outcome of one does affect the outcome of the other, meaning one probability is going to depend on that first probability that occurred. So these are dependent events. It means they do affect one another. They depend on one another. So here's an example of that. What if my two events are both drawing a card from the same deck? So what's the probability of drawing a heart and then drawing a diamond from a deck of cards? Now, a key phrase here you're going to often see is without replacement, meaning after I draw that first card, does the probability for my second card change? Well, it does. It's going to change the number of possible outcomes, because for that second card draw, I no longer have 52 possible cards in my deck, right? Because I took one out. Now there's only 51 cards in the deck, which means I have a slightly better chance. Still a ton of them, but imagine if I drew 50 cards, then that last draw, well, there's only two possibilities. Yeah. That's exactly right. That's where you usually see the with replacement or without replacement, right? You got some green marbles, some red marbles, some yellow marbles, and if you draw one out, well, now there are fewer marbles in the bag, and so your probability of drawing that next one, well, the chances are going to be even greater because there are fewer options. It's exactly what this is. And so in this situation, this event would be considered dependent because the probability of drawing my second card, well, that probability depends on my first card that I drew. That's going to change it. So let's so that's the two different types of events, independent and dependent events. And based on which type of probability is occurring, tells us which probability rule that we would use. Let me make this a little bigger for you. So here's your multiplication rule. Just like that addition rule, two different formulas based on events being mutually exclusive or not. Well, the multiplication rule, there are also two formulas, and you're going to pick your formula based on So make sure you've got these two formulas written down for independent events and for dependent events. The dot just means multiplication, and I'll explain what this vertical bar means in a moment once you get it written down. You'll also notice a slight change in the wording of the probability of these two events, whereas that addition rule had the word or in between them, whereas for these events, the word and is there. It's also a little indicator as to we do an addition or multiplying, where that addition rule is more for like a single selection occurring. Like it's what's the chances that a student passed or studied. That's still just I'm drawing one student randomly, selecting one random student. Whereas these, for multiplication rule, it's like two or more events occurring. The probability of this happening and then that happening afterwards, right in a row. So that symbol over here, probability of B, then this vertical bar A, simply means the probability of event B, probability of B, given that A has already occurred. So you're assuming that A did happen. So if event A was like drawing a red card, for example, we'll do an example. So the probability of B happening given that A did occur already. So how about what's the probability of, well, let's go with the ace and the diamonds thing again. Let's do the red card. Probability of drawing a red card. And actually, we'll make this one single probability of drawing a red card. And then and then an ace. I'm sorry, I wrote that really weird. Probability of drawing a red card, followed up by drawing an ace. So it's a probability of drawing a red card and then drawing an ace. All right, so are these events independent or dependent? Does the probability of one depend on the probability of the other? They do, right? Because there are some red cards that are aces. So first, what's the probability of drawing a red card? Well, there are 26 red cards out of 52 total cards. So that's the first probability. Followed up by the next probability of drawing an ace. Now, how many aces are there in the deck? There are 4 of them. But how many cards are left over? Is that still 4 aces out of 52 possible cards? No, you're assuming that this first event occurred. You're assuming that you did draw a red card out of those 26. You did take one out. You're left with just 51 remaining, right? There's only 51 cards remaining because you already took out a red card. What do you have left over? Now this is multiplication, which is nice and easy. Just multiply across the top, multiply across the bottom. Also in your calculator, you can just straight up multiply these out. 26 divided by 52 times 4 divided by 51. And I get 0.039. Is that a pretty big probability? No, that's pretty low. That would be approximately 4% chance that you're going to draw a red card and then draw an ace afterwards. Yeah. True, that would, because then that'd be only 3 out of 51, right? I am not going to worry about that for you this year. All right, don't worry. Additional concerns to take into considerations. Because, yeah, was that red card an ace or not? It's a good point. Go ahead and try calculating this one now, everybody, on your own. What's the probability of rolling an even number on a 6-sided die, followed by drawing a red card from a standard deck? So probability of rolling an even number, followed by probability of drawing a red card. First off, are these events independent from each other, or are they dependent? Does the outcome of one depend on the other, or are they totally separate, unrelated to one another? They're separate, right? So is that independent or dependent? Independent, good. These are independent events. The result of one of those events occurring does not affect the result of the second thing occurring. So this is just straight up multiplication. Probability of the first event times the probability of the second event occurring. So then just multiply those together. Okay. Nice. Nice. Awesome. Good. Let's divide that out again. Getting it? Yeah, just multiply them out. Awesome. Good. You got it? Yeah. Good deal. All right, I like what I'm seeing. Probability of rolling an even number on a 6-sided die. Will that be a 2, 4, or 6? Right? So there are 3 favorable outcomes out of those 6 sides on the die. How about probability of drawing a red card? Well, that's 26 possible red cards out of 52. And all we need to do is multiply these 2 probabilities together. And so 3 out of 6 times 26 out of 52 equals 0.25 or 25%. How many of you got that? Nice. All right, so when it's multiple events occurring in a row, we multiply. But you just have to consider These are independent or dependent. All right, how about this one? What's the probability of drawing 3 aces in a row without replacements? So after I draw my first ace, I don't put it back in the deck, right? I draw it and I keep it aside. Then I draw, what's the probability of drawing that second ace? Hold it aside. Then a third ace. Like I'm keeping them in my hands. What's the probability of that occurring? Now this is 3 separate events, so A, B, and C. It's still going to be the multiplication rule because they're occurring in sequence. Are these independent or dependent? Yeah, these are going to depend on one another because after the first event occurs, it's going to change the probability of the second event occurring. And the third. These are dependent events, for sure. And it's sequential events occurring, so we're going to be multiplying. Ooh, your denominator is going to be different each time. So for each of these, your numerator and your denominator are going to be different. Yeah. Is that likely to occur? That's why it's such a good hand in certain card games. So after you drew one, okay, that is the first probability. Assuming that you did draw an ace the first time, now how many are left in that deck?
3.
So that's your new numerator.
Okay.
Out of how many cards are left in the deck?
51.
That's right.
Did you multiply these?
Yep. And then you have, one more time for that third draw. You got it? Yeah, those are right. Now just multiply them all together. Well, for multiplying, you don't need to have a common denominator. So you can just type this right into a calculator. This divided by that times this divided by that times this divided by that, and just hit enter. Just one big calculation. Yeah, go ahead and multiply those 3 together. You got it. So the numerator would be how many total favorable outcomes, or how many aces are there available,
Okay.
should be your numerator. Oh, that's a small number, huh? For the first draw, how many total aces are in the deck, though? Yeah. So that should be a 4 in the numerator. Well, each of them are going to be one more than what you have written. Because for that first draw, out of the full deck, there are 4 possible aces, right? Out of those 52. Then for my second draw, assuming one was removed, how many are left in the deck for the second draw? All right, so there are 3 events occurring. So we're going to multiply these probabilities all together of each of the events. For the first event, drawing a single ace, well, there are 4 possible aces in the deck, right? So I could draw any one of those 4 aces out of the 52 total cards in the deck. Now, after I've drawn one, assuming that I did get an ace for that first draw, well, now, what's the probability of drawing a second ace? Well, are there still 4 aces available for me to pick from? No, there's 1 fewer. There's only 3 aces left in the deck. And are there still 52 total cards in the deck? No, there's also 1 fewer total cards in the deck. So that's out of 51. Assuming that those first 2 draws were aces, well, now I don't have 4 or 3. Now I have only 2 aces remaining, right? Assuming that I did get 2 aces off the bat. There are 2 aces remaining out of, well, also, if I did take 2 cards out of the deck, I'm down to a total of just 50 cards remaining. Multiply those out. And again, you can just multiply this like 4 divided by 52 times 3 divided by 51 times 2 divided by 50. And, oh my, that's a small number. 0.00018. Anyone else get that? Right? 3 zeros. So that's the probability. If I wanted to convert that into percentage, I can move this decimal 1, 2 spots to the left, and that's a 0.018% chance of drawing 3 aces in a row. What do you think? Is that going to happen? I wouldn't bet on it. You know, if you ever see like a movie where people are like playing poker and hoping for that next ace in a row, it's like, dude, not going to happen. Or more likely, if you ever watched Yu-Gi-Oh, you know, Heart of the Cards, he's always like drawing like the perfect card from his deck to win. Doesn't happen. It's not going to happen. Oh man, playing Sabak. Yep, you got it. A little cheater. That Millennium Falcon was his. Awesome. Yeah, not too likely to happen. All right, that's it. Any other questions? I have an idea. Let's practice. I have some wonderful practice problems for you in the Delta of Math. So I'm kind of combining both of these. So just kind of taught them both together. They are technically 2 separate targets, but got 4 different sections of problems for you. The first one is just like with a spinner. So there's a spinner with 15 equal areas, you know, like an old board game. It's like a circle cut up into different slices, and you spin a little arrow, and it lands on one of those, points to one of those. Numbers 1 through 15. If the spinner is spun once, what's the probability that the result is a multiple of 3 and a multiple of 5? Let's work this out together. All right, so multiple of 3 and a multiple of 5. First off, this is just one spin. So would I be doing the addition rule or the multiplication rule? Addition, right? This is just one event occurring, so that's addition rule. So what's the probability that it's a multiple of 3 or a multiple of 5? Okay, so what's the probability that I spin a spinner, it's got the numbers 1 through 15, and it's multiple of 3 and a multiple of 5? So if you want, you can think of every number. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. I'm going to know what's the probability that's a multiple of 3 and a multiple of 5. So first off, you could just instantly answer this by just figuring out what are the numbers that are both multiples of 3 and 5. But I kind of want you to use this addition rule by figuring them out separately. Are these mutually exclusive events? No. Because couldn't a number be a multiple of 3 and a multiple of 5? Isn't that possible? Oh, phone call. So go ahead and try to figure this out. All right, so what's the probability that you spin a multiple of 3? So just look through this list, which numbers are multiple of 3? Well, I've got 1, 2, 3, for 5 of them. There are 5 numbers that are multiples of 3. So that's 5 favorable outcomes divided by 15 possible outcomes. And then how about multiples of 5? Well, that'd be at 5, 10, and 15. That's 1, 2, 3 out of 15. And how many of those numbers are both a multiple of 3 and a multiple of 5? Well, that's just the 15. Now, since these are not mutually exclusive, I'm going to add up the probabilities of them occurring independently and then subtract the probability of them both occurring at the same time. So for this one, oh, wait, it said and versus or. That's going to be different. So this, all right, so you got to be careful with what it asks for, or versus and. Since it says it's got to be a multiple of 3 and a multiple of 5, instead I'm just looking for the one that meets both of those conditions. So how many numbers are both a multiple of 3 and a multiple of 5? Well, just this one, right? There's only one number. And so essentially, I'm going to bring that back. Actually has a nice diagram to show you. There's like what the spinner would look like. And it kind of did the same thing, all the different multiples. How many are both of those? 15. So there's only one out of the possible 15, so 1/15. What I was showing you before with like doing them both and then subtracting the overlap, that's if it asks or. If it asks the probability of rolling a multiple of 3 or a multiple of 5, that's when you would subtract that overlap. So you got to be careful with the words and versus or on these. Two-way tables, I had some examples with that. So you got 2 different categories. It's like the past and the studied example that I did earlier. Probability the student has an A, and so, well, how many kids had an A out of the total kids in the class? You're just doing a simple fraction there. That's just practicing reading these two-way tables that are common. This is just a more advanced version of one of those tables. So choosing a random person from town, what's the probability that they have a high school degree or some college? So one of these would have no college degree. And so subtracting those off. And then lastly, so this last one, you have to do a little bit of thinking and might have to create a little chart, a little table. So in a certain Algebra 2 class, is this us? Of 28 students. Oh my gosh, is that our class? 11, I didn't write these. This is Delta Math. 11 students play basketball and 13 play baseball. Now there are 11 students who don't play either sport. But mind you, could some students play both basketball and baseball? Could there be some overlap here? Yeah, so these aren't mutually exclusive, right? There could be some kids who do both of those. And there are some who don't do either of them. There are some that just do one and some that just do the other. What's the probability that a random student plays both basketball and baseball? Well, do we know that from the information that's given? We don't. I know that 11 play basketball and 13 play baseball. But there are also some that don't play either. So for this problem, we're going to have to make our own two-way table, like we just saw in some of those other examples. So here's what I would do for these. So you're making a table, and you're going to have, I'd break it up into threes. Okay, a 3x3 table. And just leave this first rectangle empty because those are going to be your titles, like your categories. And you've got students who play basketball and then next to it will be the students who don't play basketball. And the other column, like the rows, will be students who play baseball, and then the students who don't play baseball. Let me make sure, specify don't play basketball. So we're just going to make a little chart here to organize the different groups. Now we know we have a total of 28 students. It says 11 of them play basketball. So how many total kids play basketball? Well, I guess we're going to have a total column too. Total. So there's a total of 11 students who play basketball. So none of them play basketball. This is a total of 11, right? Now, of those 11 who play basketball, some play baseball and some don't play baseball. I don't know exactly how many of each. It also says 13 play baseball. And again, of those 13, some play basketball, some don't play basketball. I don't know how many, though. But then it says that there are 11 who don't play either. 11 who don't play baseball and who don't play basketball. So that's actually going to go right here because that's the group that doesn't play basketball and it doesn't play baseball, right? There's 11 kids that don't play either sport. That would go right there. And then I know that there's a total of 28, so that would go off here to the side. Total of 28. And so I can really just fill out the rest of this table now. Do you see like across the bottom here? If I have 28 total students, if 11 of them play basketball, how many students don't play basketball? Okay, if there's 28 and 11 play basketball, how many don't play basketball? That's 17, yeah. Subtraction, right? It's huge. 17. Likewise, over here, of those who play baseball, if I have 28 total kids, 13 play baseball, how many don't play baseball? Ooh, now we're getting good. That's right. And then you can fill out the rest of the chart similarly. So of those who don't play basketball, this has to essentially add up to 17. If there are 11 who don't play baseball, that means the remaining 6 do, right? Because that column has to add up to 17. Then like across the top, of those who play baseball, there are 13 total. 6 don't play basketball, so then there has to be 7 that do. And then same thing across the row or the column right here. There's 11 that don't, total of 15. This has to be 4. Also 7 plus 4 is 11. 4 plus 11 is 15. So yeah, it is, but way easier than Sudoku. But that's kind of fun. All right. Now we can finally go back to the probability question, which is going to be nice and easy now. It asks, what's the probability that a student plays both basketball and baseball? Well, how many kids play basketball and baseball? Yeah, that's just right here, right? That's the number of students in the class that do play both sports. That's 7. That's the number of favorable outcomes. How many total students are in the class? Out of 28. So that's your answer. All right, so let's practice making one of these two-way tables. Yeah, 7 out of 28. It might accept it. Anyways, let me try. Yeah, so you don't even have to. But check it out. It does the exact same thing that I just showed you right here in Delta Math. Make a table, you plug in the values that you know, And then just look at total who played baseball and basketball is 7 out of 28 in the class. And so it looks like you don't need to simplify. All right, that's going to be the most involved sections of questions there at the bottom. But go ahead, try working through these. We got about 10 minutes left, and I'm here to help if you have any questions. Best of luck.